How goes it? Goes. That's good. So I got some homework that I want you to work on for next Wednesday. I'm also going to write down some practice problems in case you want some extra practice. A good number of the answers are in the back of the book, so you can always check things. But just to make sure that you are on the right path to getting things done, so we'll write these off to the side while you're writing down the homework. I can get to the what I'm looking for. So I'm giving you some for practice and some to turn in, because I don't expect you to do all of these to turn in. And some of them you just might want to go back to review for exams, or make sure that you're on the right path, or if it's similar to the one that I'm asking you to turn in that doesn't have an answer in the back of the book, if you want to work one of those, that you can check to make sure you're doing it right before you do one that's hasn't had the answer in the book that you're trying to turn in. So I'm not expecting that what you turn in is enough practice for you to do, which is why I'm giving you some additional problems to look at as well. But it's up to you of whether or not you're ready to practice or not. Of course, you're welcome to ask me questions about any of the problems or any problems that I haven't suggested for practice. Hello.
Morning.
So again, the ones on the left, I want you to turn in. The ones on the right for your personal edification, if you will. And I will do this each week for the homework. I'll give you some for some that I want you to turn in and some for practice. Any questions about anything before we continue on with new stuff today, since we've talked about solving systems of equations pretty much all we've talked about for the first week of class. So today we'll get into some matrix operations. The notational side, proof side of things was on the video that I asked you to watch for today. Do a little bit of that today and more of that on Friday as well. Like I mentioned in the video, if it didn't necessarily make a lot of sense when you were watching it, that's okay. I wanted it as an introduction to the kind of things that you have to do when you're proving these things. One of the ideas for this class is make it an introduction to higher mathematics type of class. Like I mentioned the first day, linear algebra is very, very applied. It comes up in lots of different areas. So not only do we use it as a topic of study, so that you know the material before you go on to other classes, but also we use it to illustrate different proof techniques that will also come up in later classes. So one of those ideas, and you probably have a similar idea in discrete math when you take that class, when you did proofs with sets, where you had to get down to the elements of the sets. For example, if you show that two sets are equal, you take an element in one, shows in the other, and then vice versa. Right? That's one of the standard ways to show that two sets are equal. In the proof that I showed you on the video, it was showing the two matrices were equal. And it was a similar process, right? We looked at what the entry had to look like for one matrix, looked at what the entry has to look like for the other matrix, and see that they're the same. Right? So it's a similar kind of idea. Right. And like I said, we're going to do more of that as we go along, as we talk more about these rules of arithmetic that pop up in section 1.4. But before we do the rules of arithmetic in 1.4, let's talk a little bit about actual arithmetic and do some examples with numbers, because I think that'll help illustrate a little bit more what's going on with that particular proof that I did on the video. So section 1.3 talks about matrix operations and matrices in general. We've already discussed what a matrix is because we've used it to help us keep track of the coefficients when we're solving systems of linear equations. Hello, how are you? Right? We use the augmented matrix to help us keep track of the constants, the coefficients in the system of linear equations while we were row reducing. But we weren't actually doing any operations on the matrix, right? We were doing row operations and changing the matrix, but we weren't doing matrix operations, right? We weren't taking two matrices and putting them together for any particular reason why you might want to do that. So that's what we're going to focus on in this particular section. So the first operation, of course, we'll talk about is matrix addition. And I did mention this in the video as well. So when we do matrix addition, the first thing you have to make sure is that the matrices must have the same size, otherwise the operation is not defined. Or by size, we also could say dimensions. So when we describe the dimensions of a matrix, we always talk about the number of rows it has first, number of columns it has second. Okay, so when we say a matrix is M by N, we mean it has M rows and N columns. And we noticed that with what we were doing with the systems of equations, right? The number of equations was the number of rows, the number of variables, plus the one more column for the constant was the number of columns, right? Because we wrote each equation down in the rows, and across was where we put the coefficients or the variables and then put the constants on the end, right? All right, so we have to have the same dimensions, have to have the same number of rows and the same number of columns before you can add. And we also then will add, we add the entries together. And I'll say that are in the, just as using kind of layman's terms idea, that I'll just say that are in the same position, that are in the same relative position. Oops, need a verb in there. If you have done vectors in any class, where you've written the vectors with components or with i's, j's, and k's, so if you've seen Calc 3 or if you've seen physics, you've probably written vectors with components. And when you add vectors, you always just add the components, the numbers that are in the components together, right? So if you had the vector 2, 1 and the vector 3, 2, you would get if you add those together, you would get the vector 5, 3, because you'd have the 2 and the 3 together, and the 1 and the 2 together. It's the same concept when you do matrices. We've just got a rectangle instead of what you think about a line of numbers for a vector, typically. Okay. So, as an example here, if we just use particular numbers, if I say A is 1, 3, 0, negative 3, 2, 8, and B is, say, 2, negative 4, 1, 0, 2, 9. First, tell me what the dimensions of A are. What's the size of A? 2 by 3, right? There's 2 rows, 3 columns. So A is 2 by 3, so is B, right? So A is 2 by 3, B is 2 by 3. So that's the first thing that has to happen in order to be able to add, and likewise here in a minute subtract. We need to make sure that the matrices have exactly the same size. Can't add them if they don't. Just like if you were trying to add vectors, right? I can't take a 2-dimensional vector and add it to a 3-dimensional vector. There's a component missing. Okay? Same idea. All right, so they have the same size, and then when we add these two together, and I don't expect that you'll write this out every single time this way, but I want to just illustrate the process. We add entries that are in the same relative position. So what I mean is here, that 1 and that 2 will get added together because that's in the same relative position, right? They're both in the upper left-hand corner. The 3 and the negative 4 will get added together because, again, they're in the same relative position by matrix. 0 plus 1, negative 3 plus 0, 2 plus 2, 8 plus 9. And no, I don't. As you start doing this, I don't expect you to write those sums individually each time. Right? This is just me showing what happens when you do add. That make sense? Okay. So if I simplify, then you would have 3, negative 1, 1, negative 3, 4, 17 for the final answer.
So would you keep calling this A?
Oh, whoops, sorry. Nope, would not. I meant A plus B, sorry. I got excited. That's A plus B, sorry. No, I would not keep calling that A, thank you. Are we okay with the process of actually adding them? All right, and if you were doing subtraction, you would do the exact same thing. Because what is subtraction? It's adding to the opposite, right? Okay. So if you're doing subtraction, by definition, to do subtraction, I would do A plus the opposite of B, and then add, just like we would add, right? And the opposite of B would be defined by flipping all the signs to negatives. So we'll talk a little bit more about that as we go along, but are we okay with that? All right, so another operation, which is pretty straightforward, is the idea of scalar multiplication. If you've done things with vectors, now, heck, you've all done things with functions. When I take a function and multiply it by a scalar, by a number, that changes the scale, right? It either stretches it or shrinks it, if you think about it graphically, right? If I have a graph of f of x, say you had a graph of just something easy like y equals sine x, say. That would be what the graph of that looks like, right? Then if we do y equals 2 sine x, we stretch it up and stretch it down, right? Forgive my bad graphing, but that's the idea, right? It just scales it. That's why it's called a scalar. It changes the scale, okay? So you've done that with functions. If you've done vectors, you've probably done scalar multiplication with vectors as well, right? And again, that just changes the length, doesn't it? If I multiply it by 2, it makes it 2 times as long. If I multiply it by negative a third, it would make it a third as long and flip the direction, for example. We'll do more of that stuff later as well. We'll do vector stuff in here too. But the idea here is we take the scalar times the object, and it rescales the object, okay? So we do the same thing with matrices. When we do scalar multiplication for matrices, the size of the matrix doesn't matter, but say I use the same matrix that I had up here. Say this is my A, and I wanted to do, say, 3 times A. So using the same A, say we wanted to do 3 times A. Well, if you think about what you did arithmetically with vectors, if you've done vectors, you take this and you multiply every entry by that number, right? And a similar thing happens with functions. When I take the 2, when I get rid of the y equals 2 times sine of x, we multiplied every y coordinate by 2, right? There just happens to be infinitely many y coordinates that we multiplied in that case, right? It's the same concept. So we do the same thing here. We're going to take every single entry of A and multiply it by the scalar. Again, I don't expect you to show this particular step every single time. Just doing it to illustrate a point. So we would get 3, 9, 0, negative 9, 6, 24 for that one. One of the things that we will talk about later this semester is that pretty much anything mathematically you talk about, you can think of as a vector. We can think of matrices as vectors. We can think of functions as vectors. We can think of regular old real numbers as vectors if we would like, assuming that we have certain characteristics met. But it abstracts the idea of what we mean by a vector. So if we think about that as a foreshadowing idea, if I think of matrix as vector, this is kind of what we would expect to do with the scalar multiplication anyway, because that's what you've done with vectors in the past. If you've worked with vectors. If you haven't, then you can ignore everything I say about vectors, because we'll talk about it later. But if you've worked with vectors in the past, that's exactly what you did with vectors when you did scalar multiplication. So it shouldn't be a surprise. It's the exact same thing we do here. At least I don't think it's a surprise. All right. Let me do one more operation that requires a specific idea for the matrix. So this is the idea for the idea of the trace of a matrix. We'll do multiplication in a minute. Multiplication for matrices is weird if it's the first time you've seen it. That's what I illustrated with the proof in the video, which is another reason why I wanted you to watch that particular one, because matrix multiplication is kind of odd. But there's a reason why we do it, define it the way we do. And mainly it's because of application ideas. But let's do trace first. So if we're doing the trace of a matrix, this requires something about the size. This requires what we refer to as a square matrix. So matrices in and of themselves are rectangular. Right? We have fixed number of rows, we have fixed number of columns. So they're rectangular. So when we say square matrix, of course, we mean that the number of rows and the number of columns are the same. So a lot of times we'll write that as n by n when we say square matrix, just to illustrate again that we have the same number of rows as we do columns. When we do the trace, it requires a square matrix. So if I can't use the A that I had before, so let me define a new matrix. I say C here. I'm going to make it, let's say 2, 1, -3, 5, 7, 0, 8, 2, -4. What size does C have? What are the dimensions of C? 3 by 3? Good, okay. So that's definitely a square matrix. So when we do the trace, there's something specific that we need to identify in this matrix to be able to do what we refer to as the trace. So what we need to identify here is what's referred to as the main diagonal. And this is the part that I'm going to circle here. And this is why we require a square matrix. So what I just circled here is what's referred to as the main diagonal. There is also another diagonal in the matrix, right? Actually, there's several, but there's another longest diagonal that you can make. Okay? That one I typically refer to as the off diagonal. Not as important as the main diagonal, because we do things with main diagonal stuff later on as well. But this is referred to as the main diagonal. We'll identify this later on with general entries of matrices as well, but right now just know that it's the main diagonal. When we do the trace, and we define, or the notation for trace is just TR of the matrix, so this will be TR of C. The trace is just the sum of the main diagonal entries. So it's just 2 plus 7 plus -4. So the trace here is the sum of the main diagonal entries. All right, so one of the reasons why I wanted to do these three operations first, besides the fact that you need to know how to do them, Not that any of the ones that we've done are extraordinarily hard arithmetically, right? If you understand how to do it, the arithmetic, it's just arithmetic and it's fairly easy, right? By the way, all of these things are also built into your calculators. You do all of these things. Oh, there's one thing I forgot to tell you that's a weird thing in your calculator. And I'll mention that in a second. There's a weird thing in your calculator when you do row reduction. I totally forgot about it until just now. That pops up. That might actually be important later. You'll see a weirdness later on. Not today, but it might be something that pops up later. I want to make sure I mention it. But these are all different types of operations on matrices that either the result is something different than you started with, or you take two objects that aren't the same type of object and put them together. So the first thing we did was matrix addition, right? Which, okay, so I took two things that looked the same, put them together, and got something that looked like the other two, right? I took two matrices, put them together, and got another matrix, right? Okay. The second thing we put two things together that didn't look alike to start with, right? I took a matrix, and I took a number, and I put them together. Those are things that don't look the same to start with, right? 3 doesn't look like a matrix. It's not. It's a number, right? So that's an operation between two different type of objects and putting them together. Okay? Now, both of those are examples of what are referred to as binary operations, taking two things and putting them together and coming up with a result. That's a binary operation. Okay? This last thing is not a binary operation, right? It only took one input. So it's referred to as a unary operation. U-N-A-R-Y, unary operation. It requires one thing to put in and gives you something else out. Now in this unary operation, I put in a matrix. What kind of a thing did I get out? A number, a scalar, right? I got out a number, correct? So this takes a matrix and makes it into a different object, right? Starting with a matrix, ending with a number. We're going to have all sorts of different ideas, different things that do these kinds of things. We're going to do other binary operations. We're going to talk about matrix multiplication here in a second. But we also will do matrix inverse, which is another unary operation. Because I would take a matrix and its output will be its inverse. We'll talk about that later. We'll talk about that in the next chapter, or the next section, I mean. But the whole idea of this is I want you to get a little bit more familiar with the idea of we're really taking objects and changing them to other objects. There's some function idea here that's going on. Okay. I know I'm making a big deal out of what seems to be something that's not very hard, and obviously, I hope taking the trace of a matrix is not something that's very hard. Okay? But again, I told you one of the points of this course is to get you introduced to higher level mathematics, and there are other things that go on in higher level mathematics, which is why I'm trying to illustrate these points as I go along. All right, well, let's go on to are there any questions before we do matrix multiplication? We okay with this? Okay. All right. If you've seen matrix multiplication before, you probably already know how to do it. But if you haven't seen it before, the idea is kind of weird. At least I think it's kind of weird. All right. So really, one of the applications for doing matrix multiplication is to understand how different things can interact with each other and try to observe long-term behavior based on these interactions. So what I mean is, let's say, I'm going to illustrate this hopefully by example, and then we'll talk a little bit more later, way later on, about what I really mean here. But let's say you've got two different states that something could be in. Whatever that happens to be. Say maybe this is a weird example. say you've got a mouse that can go into one of two compartments at any given time. Okay? And it moves randomly depending on its width. I want to go over here, I want to stay where I am. Okay? So we could say that at any given time we have probably say we come in every 10 minutes and see where the mouse is. Is it in room 1? Is it in room 2? Okay? There's going to be a probability, like I said, the mouse is going to move randomly, so there's going to be probabilities associated with whether or not it's in room 1 or in room 2 based on where it starts. Okay? So obviously it could stay where it is, or it could move to the other room, right? And if it started in 1, it could stay in 1 or go to 2. If it started in 2, it could stay in 2 or it could go to 1, right? Those are just graphically, that's possibilities, right? We agree? Okay. So one of the things that you might want to do, let's say I associate some probabilities here. Let's say that, I'm going to make up some numbers. Let's say that the probability that stays in room 1 is 0.2. The probability that stays in room 2, if it started in room 2, is 0.3. And if you're familiar with probabilities, then of course, if it's probably it stayed in 0.1 and 1 is 0.2, it's probably that it moved. 0.8, because it has to be the rest of it, right? It has to add up to 1, it has to be 100% chance, right? And then likewise, what's the probability if it started in room 2, it went to room 1? 0.7, right? Now, this is a nice diagram to kind of see what's going on, but mathematically it's hard to analyze a diagram, right? So a way that we might keep track of this is just with a matrix. Say that rows and columns correspond to what room it's in. So here's this refers to where it starts. This refers to where it ends. Okay, so I could put a 0.2 here. I could put a 0.8 here. I can put a I need to put here 0.7 and 0.3. Right? I could keep track of it with a matrix this way. Now, one of the things, like I said, we might want to know is long term, where does the mouse end up a certain percentage of the time? Or where does it end up after two cycles? So let's do this from an analysis standpoint and see why we might want to multiply the way we're going to multiply. All right, so let's say the mouse starts in room 1, and I ask you for the probability the mouse ends up in room 2 after 2 time periods. Oops. Let me get to scroll. So the diagram and the matrix are telling us the probabilities that it's after 1 time period, right? So all we've done is just written it in a nice form, in a rectangular array. Square array, in this case, but right, that's all we've done. It's not telling us the probability that we end up in the room after 2 time periods, but we can figure this out, right? So, let's see how that works. Okay? So, we'll let the probability of the mouse, let's say, just for argument's sake right now, let's assuming that it starts in room 1. So assume that. Let's just do that one particular thing. And then we're going to talk a little bit about why the matrix multiplication that we're going to do works the way it does. And then I'm going to go away from this example and come back to this idea later on in the semester. Because the type of analysis that we need to do on this requires some more theory that we don't have yet. All right, so let's think about this. So it starts in room 1, And we're going to move, it needs to move to room 2, but it's after 2 time periods. We're going to observe it after time 1, and then observe it again after time 2. Okay? All right, so what are the possibilities for it to get to room 2?
Either loop around back to room 1 and then go to room 2.
Okay.
Or you can go to room 2 first and then go back to room 1.
Okay, good. Yeah, if it starts in room 1, there's basically 2 ways you can go, right? It can stay in room 1 and then move, or move to room 2 and then stay. Those are the 2 ways, right? So, if you know about probability, if I stay in room 1, that probability is 0.2, and then move to room 2, that probability is 0.8, right? We agree? Okay. Or we could move to room 2, and then stay in room 2. Oh, we're moving. Yeah, I did that backwards, didn't I? Sorry. Right? Thank you. Okay. So let's think about, so we started in room 1 and ended in room, this is started in room 1 and end in room 2, right? Let me put this matrix here side by side. All right, so this is over here. This is where it started, right? That's what I told you. Started in room 1. Ended in room 2. That's the second column. Notice that this operation that we have here looks like I took this 0.2, bear with me, I'm in this row and this column essentially, right? This is where it starts, this is where it ends, right? Here, it took this 0.2 times that 0.8, right? Took this 0.8 and multiplied by that 0.3. We've matched this row to that column, right? And then added the 2 together. You agree? Okay, we matched this row to that column and added the 2 together. So when we do this multiplication, this number up in the right-hand corner, what is this? This is 0.16 plus 0.24 gives me 0.4. It's 0.4. All right. Okay. So let's think about how the other entries would pop up. And again, so this result is started in 1, ended in 2 after 2 time periods. Right? Let's think about how we would get the other one. If we wanted the starts in 1 and ends in 1. Well, how can you start in 1 and end in 1? You can go to 2 and back to 1, or you stay in 1 both times, right? If I stay in 1 both times, what would you multiply together? 0.2 times 0.2, right? If you go to 2 and then back to 1, what would you multiply together? The 0.8 times the 0.7, right? Notice again here, what did we do here? How did I say we got this 0.4? It was that row and that column and matched it. Notice in this case, if I took this row and this column, that's exactly what we would do, right? 0.2 times 0.2, that would be loop around in 1 both times. 0.8 times 0.7 would be move to 2 and then back to 1 and add it together, right? Do we agree with that? Yeah. Okay. So you get 0.04 plus 0.56, I think gives you 0.6, which is better, right? Because you're either in 1 or 2. Those have to add up to 1 in the rows. And then you could do the same idea, right? If I start in 2 and end in 1, it would be I moved to 2 and then stayed in, or I moved from 2 to 1 and then stayed in 1. Or we moved to 2 and then stayed, we stayed in 2 and then moved to 1. Same idea, right? And likewise. So this is one of the reasons why we define matrix multiplication the way we do. And I'll fill in the other numbers here in a second. But if we've got operations that talk about moving from one area to another, and we want to analyze long-term behavior, I have to do this matrix multiplication idea. We've got to multiply these things over and over and over and over again and see what happens in the long run. But to do this multiplication, I don't multiply entry-wise, right? I've got to do this odd thing of match a row to a column and do essentially what's a dot product of vectors, if you've seen vectors again. Okay? So that's how we define our matrix multiplication. If I filled in the rest of these numbers, you would get 0.14 plus 0.21 is what, 0.35? And then I'd have 0.56 and 0.09, which gives me 0.65. You can check those numbers. But these numbers match up with probability. So this is just one application of what we can do with matrix multiplication. Okay? This is why matrix multiplication, well, not this specific example, but in general, this is why matrix multiplication is defined the way it is. And it's not just entry-wise. Okay? So, let's do that. Let's do another example. By the way, this is an example of what we refer to as a Markov process. And Markov processes, Markov chains have lots and lots and lots and lots and lots of different applications. The other Dr. Stickles wrote an article about analyzing the 3 strikes game from The Price is Right using Markov chains. So, pretty fun, this is fun stuff. Oops. If you do actuarial science, you'll see Markov chains. If you do, they pop up in biology because there's lots of discrete dynamical systems in biology. The reason why it pops up in actuarial science and in finance as well, it's because it's probability theory ideas. All right, so let's talk about matrix multiplication. So we notice that, like I mentioned before, I had to match up the row of the first matrix with the column of the second matrix, right? If I match up a row with a column, that means that as I go across the column for the first one, I have to go down the row for the second one. So the number of columns of the first have to equal the number of rows of the second. Okay? So these two numbers here have to be the same. Okay? Can't do matrix multiplication if those two don't match. It's just undefined. Okay? The result is m by p. So it's the number of rows in the first one, number of columns in the second. That's the answer. That's the size of the answer. So let's do an example. Let's say our A is 3, -1, 0, 2, and 5, 4. And our B is, let's say, 1, 8, 2, 6, 7, 0, 1, -1. Size of A? 3 by 2. Yeah, I gotta do the rows first. A is 3 by 2. B is 2 by 4. So which operation can we do? Can we do A times B or B times A? Or both? It's just A times B, right? The number of columns in A matches the number of rows in B, but the number of columns in B do not match the number of rows in A, right? So just to emphasize that, AB is defined, but BA is not. So right away, you see a difference in matrix multiplication than from real number multiplication, for instance. I can't necessarily even multiply in both orders, right? I can multiply one direction but not the other. That's weird. Yeah, Megan.
Why can you do A times B without B times A?
So the number of columns of A has to match the number of rows of B.
Oh, okay. I thought the rows were.
Yeah. The number of rows, the number of columns here, the number of rows here. So A times B is defined, but I can't do B times A. So that's weird, right? To start with. Usually you're used to being able to multiply in either order. Can't necessarily do that here. Even if they are both defined, it doesn't mean the answers will be the same either. We'll do an example of that here in a second. Okay? So let's just do this operation. What size will A times B have in this case? 3 by 4, good. Right? Give me some room here. At least to write out a couple of these. All right, so to get this upper left-hand entry, so to get the 1, I'm just going to put these numbers here for reference sake. They're not part of the answer. Okay? To get this upper left-hand corner entry, to get row 1, column 1, I have to take row 1, which is here, and multiply by column 1, which is here. Those are the two that we match up. Okay? So we'll have 3 times 1, right? The 3 times the 1, and then plus the negative 1 times the 7. Everybody see where I'm getting those? I'm going to circle this in red here, just to illustrate. Okay? Visual, my brain, when I do this, I actually have to visualize it turning. I'm not a very visual person to start with, but for me, I have to kind of think about it turn. Okay? I visualize this thing getting spun and being set next to it. Right? Just take it 90 degrees and match it. Okay? So 3 times the 1, negative 1 times the 7. Matter of fact, if you see me doing this in my office working on a piece of paper, I'll actually turn my fingers and go across so I can visualize it. I don't know why, it's just my brain is wired weird. You've probably already guessed that by now. Negative.
So if you were to do that, like the 7's in the 1 place, kind of, you multiply the 3 times the 1.
So I do the 3 times, say that again? Sorry.
So if you were to like rotate it,
so I'm rotating this one to match it with that one? Mm-hmm. Yeah.
I don't know, I guess my question is you're not multiplying the two that are in the same position, you're multiplying it by the other position?
Well, I multiply so if they are in this, I think of them in the same position because I think about reading this one left to right, versus this one being top down. So as I go left to right, I go top to down. So that's how they're in the same position. Does that make more sense? All right, so what would the next entry across be? If I go over here to column 2, oh hey, it's still red.
3 times 8,
okay.
1 times 8.
Okay. So I've got to take that 3 and I match it with that 8, and I take the negative 1 and match it with the 0. Do you see how it's, by the way, if you've seen vectors, do you see how it's a dot product? What will be the next one over? 2 times 2, negative 1 times Careful. So, yeah, it's times the 1, right? Because we're taking this, doing those two, right? The ones I just highlighted in yellow. Might as well use my colors while I got them. One of the reasons why to use this, right, when I'm lecturing as opposed to the chalkboard. Let me move over my bracket here a little bit. Oh, hey, that's not black. What will the last entry be then?
3 times 6 plus 1.
Good. Anybody not seeing where these numbers are coming from? Time to ask is now, right? It's not like matrix multiplication is going to go away. All right. Notice how, as I'm going across this row, notice how the first two numbers that we did the multiplications with didn't change, right? It's the first row each time. Right? Notice what's changing is as we go across the columns, right? I used column 1 for the second one, then column 2, then column 3, then column 4. Right? So you can match it up that way as well for the next row. Notice in the next one you would have 0 times 1 plus 2 times 7, right? Notice because the 0 and the 2 are the second row here. So we've matched second row with first column with the 1 and the 7. So I would have 0 times 8 plus 2 times 0 for the next one. Right? I would have 0 times 2. Whoops. What did I say? 2 times 0. Sorry. I would have 0 times 2 plus 2 times 1. I would have 0 times 6 plus 2 times negative 1. If I look down from first row to second row, the only thing that should have changed were these first ones. Right? And by the way, you can do this on your calculator as well if you have A and B typed in already. You just put A next to B and it'll multiply them together just fine. Or tell you it's not defined if it's got the wrong number of rows and columns. So you can always check these on your calculator. So the last one, without me writing all the products down, I would have 5 plus 28, which gives me 33. I would have 40. I would have 14, and I would have 26 for the last ones. You can check those. If you've seen matrix multiplication before, then you were probably bored to tears with my description there for that long, because you already know how to do it. But if you haven't seen it, that's why we want to make sure that I went through and explained where all these different numbers are coming from, because it's weird. The first time you see matrix multiplication, it's weird. I think it's weird. I thought it was weird the first time I saw it. Okay? It's not how you would think to multiply two matrices together if you were just inventing it yourself. Right? Because my guess is if you were thinking about it yourself and trying to invent it yourself, you would have done it like you did addition. Right? Just take the pieces that match up and multiply them together. But that's not how we do matrix multiplication. Okay? It's one of the reasons why I wanted to take some time, give you an example of why we care about multiplying this way. That was why I did the probability example. Again, I don't expect you to reproduce that now. I wanted to give you some motivation behind why we wanted to do matrix multiplication in this, what seems to be a weird way. Okay? By the way, if you've had discrete, you've done some graph theory things, you can apply these techniques with matrix multiplications to how many different paths are between two vertices in a graph. That's another application of doing matrix multiplication. Okay? So, again, there's reasons why we do it this way. Okay? So we'll do more of this. We'll get into playing around with the elements. We'll talk about the next section as well, where we the rules of arithmetic. Start doing some inverse stuff as well. So have a good one. We will see you on Friday, if not before.